Alright, this is going to be an example of a energy orbit problem, an orbit with energy, and I'll kind of explain it. Hopefully, it'll make sense by the end of it. Astronomers are trying to send a satellite into an orbit of Halley's Comet about the Earth. To start, they will send the satellite into a circular orbit with a radius equal to Halley's Comet's perihelion distance. This distance is 88 million kilometers. The radius of the Earth is 6,378 kilometers. Mass of the Earth is 5.97 times 10 to the 24th kilograms, and the mass of the satellite is going to be 5,655 kilograms. So what's basically going on is that we want to like sort of recreate Halley's Comet about the Earth. So we're going to send a satellite. We're going to kind of pretend like the Earth is the sun, like that's what the astronomers are doing. And then if we model Halley's Comet, it would have a perihelion distance, which is the distance closest to the sun. I'll do it in blue here. So the distance closest to the sun is going to be this distance right here. Obviously, we're just going to have the Earth be the sun, and that's what the astronomers are trying to do. This is going to be a radius r, right? We're going to orbit with that perihelion distance, and the actual orbit would kind of be like this, where this is the closest approach to the Earth. 88 million kilometers. So how much work on the satellite is necessary for such an orbit? Well, obviously in a circular orbit, there's gonna, the satellite is gonna have some energy, and that energy we derived actually in the last video. So definitely check out the last video. The amount of energy in a circular orbit is equal to negative 1/2, actually I'll do it like this, negative g m1 m2 over 2r, or 1/2 negative g m1 m2 over r. So we know the mass of the Earth, which is like the thing that it's going to orbit. We know the mass of the satellite, and we know this distance. So we just got to figure out the change in energy. That's work, right? So E initial, whatever the initial energy is going to be, plus the work is going to equal E orbit. So the initial energy. Well, what initial energy is the satellite going to have? It's on the surface of the Earth right here. So there's going to be some UG, some negative UG, but UG nonetheless right here. So all the energy is going to be stored initially as UG. So we can, our equation for UG is just negative G M1 M2 over R, plus the work done is going to equal E orbit. So now all we really got to do is just add in this case, subtracting a negative, add this to both sides. So the work is really just going to equal negative G M1 M over 2R plus G M1 M2 over R. And if we're going to add fractions, we got to have the common denominator, and then you can figure out the work is going to be equal to Gm1 M2 over 2R. That's how much energy we need. And I'll plug in all the values to get an actual number, but one thing I kind of want to mention, something that's pretty cool, is it's the initial energy of the satellite. It's not just UG, because the Earth spins. Maybe you caught on to that, or we're thinking to yourself, yeah, isn't there some kinetic energy with the spinning of the Earth? And yes, it's going to be moving at a certain speed, and then there's going to be, if we were to sort of algebraically do this, the initial energy is going to be UG plus 1/2 mv squared. 1/2 mv squared for the kinetic energy, and then right when we're solving for work, we're going to do minus 1/2 mv squared. So we're subtracting, which means there's going to be less work. It's going to be less energy in this, which makes sense, right? If it's already moving, we don't need to add in as much energy. That kinetic energy will kind of help us, assist us, kind of boost us there. That's why they actually send like satellites in Florida, because when you're like closer to the equator, you're moving faster, right? Because the rotational velocity is the same at every point of the Earth. So bigger r, right? Bigger radius from the axis of rotation, you're going to be moving faster. It's going to take less energy. So that's a pretty cool thing. We're not including it just because, I'm lazy. We're just going to hope that the Earth is not spinning today. we're going to just now, I'm just going to plug in everything I know. 6.67 times 10 to the negative 11th times m1, which is the mass of the Earth, right, what we're orbiting, 5.97 times 10 to the 24th, times the mass of the satellite, which is 5,655. Divide that by 2 times, now the radius, remember, it's in kilometers, so if we want this, unit to be joules, right, we got to make sure this is meters, so just do add on, like do 88 times million, so million, that is 6 zeros, and then you just want to tack on 3 more zeros after that, right? Yeah, 3 more zeros, and then you will get the work is going to be, the work necessary, I should say, for this little thing. Let me get I'm losing track of my markers. It's actually really bad. It's going to be, I think that's 1 million, 12 million. I got 12,794,405.37 joules. So that's how much energy you would need, probably in terms of fuel. And yeah, let's just, and then you can very quickly find out how fast you would need to be moving. So that's pretty cool. Now let's get on to the next part. Now that we're in the circular orbit, the satellite will briefly fire its thrusters, sending the satellite into the actual orbit of Halley's Comet. How much energy is necessary for this? And the eccentricity of the orbit of Halley's Comet is 0.97. So what's going on in this part is that, hey, we're moving, and then right here, like, right here, or, whatever, right here, the way I've drawn it, you would fire your thrusters so that you'd be moving really fast, and then you can kind of sort of escape that gravitational field to an extent, right? Because you're going to start heading back, but then you will be able to get the actual orbit of Halley's Comet. In the last video, we derived that for an orbital, what am I saying? Elliptical orbit. Why am I using, I wanted to keep this consistent. I don't know why I'm using blue. This is a marker I want. So it's going to be the orbit in like an ellipse. For an elliptical orbit is going to be negative g m1, m2 over 2a, where a is the semi-major axis of the ellipse. Okay, so yeah, you can watch the last video to see how I derived that. I had to use conservation of angular momentum, conservation of energy to derive that. But you might be thinking, okay, it's just 2a, so let me just take a, which is 88 million times, in meters. We're going to put that in here. Wait, that's the same exact number as this. You don't need any work. Which doesn't make sense, right? Because you got to fire your thrusters. That's going to take up your fuel. You're going to need energy. There's going to be work done on the satellite. So why didn't this work, right? If I put in 88 million, well, A, right, that's the semi-major axis of the ellipse. That is, if this was the center of the ellipse, this is A, right? And then the other A is right there. So this distance is obviously not equal to that. So what we're going to do, is we're going to do the same thing we did last time. E initial plus the work is going to equal E final. So the work is going to equal E final is going to be negative G M over 2A. And remember, the final energy is going to be kinetic energy and UG, but we derived that when you add, in an elliptical orbit, when you add the kinetic energy plus the UG, it's always going to equal this. So we're going to do plus, and now, once again, the E initial is, and for the circular orbit, it's initially kinetic energy and UG, but remember, when you add it, it's going to always equal G M1 M2 over 2R, right? And it's going to be negative, so I'm like adding it. And that's going to be the necessary work. But yeah, we just got to figure out what A is. And that kind of becomes a geometry problem, because if you were to just draw the ellipse in a better way, like so, if this is our sun, which is at the focus point of the ellipse, this is R, right, our distance. This is the center, and this is C, which is the distance from the center to the focal point, sorry. So the semi-major axis, right, if this is the center, it's just going to equal C plus R, right? A is equal to C plus R. Now, We don't know C, but what we do know is the eccentricity. So the eccentricity is always equal to C over A, and then C is therefore equal to E times A. So A is really going to equal C plus EA plus R. So for solving for A, we're going to get A is equal to, we're going to do A minus EA, get all the A's on one side, and then we can actually just factor out the A. We get A times 1 minus E, is equal to R, so A is equal to R over 1 minus E. So now we know E, we know R, we can just figure out A by just plugging it all in. So we have 88 million, which is our 6 zeros, right? Yeah, 6 zeros times 10 to the third. And then we would get that same, with 3 zeros added on, converted to meters, minus, or divided by 1 minus E. So 1 minus 0.97. It's going to be a really big number because, 1 minus 0.97 is very close to 0. So dividing anything by 0, close to 0 is going to give you a big number. Now, you should have gotten 2.93 times 10 to the 12th meters. What we can do now is just plug that back into here. So I'm going to just quickly do that on my own. 6.67 times 10 to the 6.6, negative. Negative 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24 times, we're multiplying by the mass of the satellite, 5, 6, 5, 5. Divide that by 2 times this. I'm just plugging everything in here. If we're thinking about this being a derived equation. And then, oh, I'm so sorry. This was my mistake. Don't put a 2 here. It's just R. Because that's the equation for UG. Oh, wait, no, what am I doing? This is not UG, we're doing total energy. Okay, sorry about that. So, then, you're going to multiply, you're going to subtract that. I know this is taking a little bit of time. I'm just trying to sort this out. You will get your final answer. I'm sorry for the time. I probably wasted like a good few minutes. It's going to be 12,410,573. So 12,410,573.21 joules. This 0.21 joules makes all the difference when you're thinking about fuel and all that stuff. So yeah, there you go. That's about orbital transfers, transferring between these orbits and all that fun stuff. Thank you for watching.